All right, so hello everybody. Thank you very much for having me. I know it's hard after the lunch, and there's been talks and talks and talks this morning, and yet another one. So I'm going to be talking about summarizing some of the work that we've done together with some Intel researchers lately on embedded learning and some of our work that we've been doing on building the skeleton of a neuromorphic framework. So what we are interested in this project, which we did in collaboration with Intel, as I said, and also UCSD, is to reduce the task energy requirements, or basically increase the efficiency. And this energy per task can be basically divided trivially into two parts. One which is the energy it takes you per unit of operation, be it synaptic operation or a multiply accumulate, and the number of operations you require to solve that task. So optimizing on both ends would basically improve the overall task efficiency. So this talk is mainly going to focus on the software aspect, which is trying to reduce the number of operations for a given task. Given that the particular operations that we'll be using are those, in particular in the neuromorphic platform, where the energy per operation is potentially low, right? So we're thinking in the picojoules per synap, and my former postdoc advisor, Gerd Kahnberg, was particularly optimistic here in talking about the femtojoules per synaptic operation. So if we can build algorithms that can use these types of operations and not require too many of them, then we're in the game. So next slide, I'll talk about why embedded learning. But one thing to realize here is that embedded learning will, by definition, reduce the energy per operation, right? Because you're doing the learning on chip. Okay, so as I said, this talk is going to focus on the software aspect and the number of operations per task for low energy per operation platforms. So we've spoken a lot about online learning. It's not evident to many why you would want to do online or even embedded learning. So I think there are three reasons here, some of which we've discussed in length, others not. So obviously the first one, as I mentioned, is it reduces the energy required for learning, which at least in the case of deep learning, this is one of the most energy intensive steps in the lifetime of a particular neural network or algorithm. Okay, so I'll give you some of the models that we developed, in fact, to promise low power learning. The second here is the compensation for device non-idealities, right? So I come from the more classical neuromorphic engineering field. So I did my PhD in Zurich with Giacomo Indiveri, who himself was involved with all the carbon meat people. So I worked with analog hardware. And one thing I learned there is that you can't do anything if you don't compensate somehow for that for the non-idealities. Okay. So if we have embedded learning, basically embedded learning is going to play the role of a calibrator or compensator of the device nonlinearities. In fact, Johannes Schemmel mentioned this also in their plasticity, embedded plasticity unit for compensating for the non-idealities in their hardware. It's also very important for, there's a huge community, of course, working on using memory stores or resistive RAMs for in neuromorphic computing. And there, the way that these resistive RAMs are programmed now is itself basically an iterative procedure for RRAM per RRAM. So it's very inefficient. But if you introduce this learning on the device, and it's learning all the time and compensating for the eventual drifts in the hardware, then I think that's where embedded learning can be very useful. Of course, another one is in this idea of lifelong learning. That, of course, you can have a model that is learning all the time. Right? This also gives you the ability to do active learning. So that means to take particular action in order to seek the data that would maximally reduce your error at a certain task. So there's many instantiations of these. Some are called active learning, adaptive learning, active inference, active perception. So embedded learning is something that will enable you to do it on hardware in an efficient manner. Okay, so applications, I think these are, most of them are obvious. So of course, mobiles and wearables are obvious targets. Autonomous vehicles. This is a tiny drone that my former office mate Jörg Conrad built with a small silicon retina on top of it. So if you can actually build a hardware that can directly process the data on this tiny quadcopter, then I think that would be a really interesting system. The third one is a little bit less obvious. So because of the cost, both in data set and energy and hardware requirements, I guess, of training a model, what we mostly have is a one-size-fits all, right? So I don't think many of us actually trained a VGG network or Inception, or in fact, I never went through the trouble of doing that. Instead, I just download the weights that are provided to me. And so having personalized models can be very interesting from a security point of view, right? Maybe I don't want to share all my photos with other people. Even models that extract the gist of it, maybe I don't want to share that information. Or in the biomedical field, for example, there's a lot of sensitive information with respect to health, right? And you still want to build a model. This is a particular example of this. This is a patient with a glioblastoma, and this is work of Dan Chen at Notre Dame, who's basically doing using a deep neural network to classify the neurons, and I think these are neurons or astrocytes, I can't remember. So embedded learning would probably, of course, greatly reduce the energy for doing this without having to communicate it to a mainframe. And I was just doing back of the envelope calculations here. If everybody in this country trained their AlexNet, so that's 300 million people, that would correspond to 5% of the electricity production in the country. Right, so that's, of course, no, we're not going to have, we don't need to have 300 million AlexNets, but if you think of these biomedical applications, that's somehow possible. And of course, they don't train it once because you have to basically do a hyperparameter search. So. Okay, so why neuromorphic engineer? I'm preaching to the choir here, but I'd like to reintroduce this for the rest of the talk. I'm mostly interested from the architectural aspects of the brain. And here, the fact that essentially neurons communicate with very temporally and spatially sparse events. So in this case, we have these spikes that are essentially transmitted to a different chip or a same chip, but the transmission is mediated through this fast bus where the addresses of the target neurons are written. So this is great in terms of parallelism, right? So there's very little information that is actually transmitted between these different cores or neurons, whatever you want to call it. All the other parameters like weights or internal states or synaptic tags, whatever you want to think is useful for the algorithm, they remain local. This is great, but we don't really know how to use this kind of architecture for practical workloads, right? So we need to find algorithms that can operate on what we call local information, right? So local information here is going to be weights, internal states, and so on. I think so Mike Davies touched to this point earlier. Okay, so how can we build algorithms that use local information? So in deep networks, or in neural networks in general, so the weights, the deep weights, they actually, they may require non-local information, which can be, for example, targets or error. And just to precise a little bit what Mike Davies said today, so backpropagation from certain aspects can be a local learning rule or can be non-local. What makes it a particular algorithm or operation local or non-local depends on the particular substrate. So if you're doing backpropagation on a GPU, this is largely local, right? But if you're doing backpropagation on a neural substrate, it's not local. Okay. Pierre Baldi, who is also at UCI, formalized this idea of what you need to transmit into these deep weights in order to learn. So we call this deep local learning versus local deep learning. And he had this great paper that I highly recommend that describes that basically backpropagation requires a certain number of symmetries. Right? So again, particular hardware may offer you those symmetries, in which case backpropagation is local. But he also shows that you can break some of these symmetries. And these particular algorithms, they go by different names. They have random backpropagation and feedback alignment, and adaptive feedback. And so there's really different names to it. But the bottom line is that you can break these symmetries and still do a relatively good job. There are other techniques of interest of how can you learn these deep weights while still being local. I really like this idea of synthetic gradients or decoupled neural interfaces that from DeepMind. The idea is that you have this local network that generates gradients without having to wait for the output neurons to spike in order to transmit the error backwards. It requires an external loop that trains these gradient generators. What this does is still it does break the kind of the temporal synchronization requirements of backpropagation. And later today, Hesham Mostafa will talk about a somewhat related method to synthetic gradients, but which is totally local and using these local errors. So I think that's a really interesting way to go forward. This is to keep in mind is that backpropagation is actually optimal in the space of learning algorithms. That's something, again, that Pierre Baldi demonstrates in one of his papers. So anything you do is going to be slightly worse. So the take-home message here is that several architectures for deep local learning are possible if the best possible accuracy is not your goal. And I think I would argue that this is perfectly valid for us because in neuromorphic hardware I think is most interesting when it's applied to a dynamic environment. And in a dynamic environment, you are not even going to have the time to reach that best accuracy, which usually takes a lot of time. Okay, so what is our approach to this? So something that hasn't been mentioned too much in this workshop is, and one of the success stories of deep learning, I think, was their software approach, right? So the idea of using TensorFlow and gradients and so on. So let me just take a step back and extract what's deep learning and what's the basic approach that people use in machine learning and deep networks. So we have some objective function, right? We can almost always describe a task of interest in terms of an objective function that we want to maximize. So, and let's write this in terms of a neuron model, some neuron model that we could actually have on a piece of hardware, for instance, Loihi or the brain scales hardware. So there has been a lot of research in actually modeling neurons. This is one that I really like. So this is by Wolfram Gerstner, the spike response model, which just basically it gives you the probabilistic, the probability of a neuron being active and giving its membrane potential. And the membrane potential is the usual suspect. That's basically the sum of its PSPs. Okay. So if you look at this is actually very similar to what an artificial neuron is, right? So you have some output, and it depends on the sum of inputs. Of course, in this case, they're convolved over time because the neuron is a dynamical system. So from this neural model, what you can do is you can take derivatives and essentially extract a learning rule, right? So this gives you the delta W or in continuous time. So this would give you the infinitesimal change of the weight, and it's the derivative of the weights, which of course is by the chain rule is going to involve the loss, the derivatives of these activation functions, and the derivatives of the membrane potential. So this is essentially just repeating what something like TensorFlow or even just what you would do mathematically in a deep network, but using basically neuron spiking and potentially spiking neurons. And I like to point to the fact that this learning rule is not really SCDP. I mean, there's been a lot of discussion about SCDP here, but if you look at this, it doesn't, I mean, there are obviously some parts, so this part here depends on the presynaptic neuron, this depends on the postsynaptic neuron, this is some sort of modulation, but this doesn't really take the form of a proper SCDP rule. So why SCDP, right? So here's what you can do. You can take this rule, or you can take neurons that are configured with this learning rule and just do the classical Bien-Pou experiment. This is what Jean-Pascal Pfister and colleagues did in their 2006 paper, where they tried to find the optimal learning rule. And they do find an SCDP learning rule or a learning window that looks like this, these classical exponential windows. Right? But that is not to say that if you go in hardware or in a software and you implement this SCDP rule, it's not going to give you the right results, right? It's like saying like a cup is somewhat round instead of cylindrical, so anything cylindrical is going to be able to hold water, right? So it's just, SCDP is just a measurement of what of the real biological plasticity rules. So why do people, including myself, go through the trouble of implementing SCDP when neither biology or machine learning tells you that you have to do this? It's really a question of efficiency in digital, and mostly in digital hardware, that essentially if you have SCDP allows you to do event-based, to reduce plasticity to an event-based process, so you only update the weights when you have a presynaptic or postsynaptic event. It also reduces the amount of memory that you have, that you need to have. So we're doing SCDP because we can't do otherwise. If you have hardware that is where the synapse is a continuous dynamical system, that you have some control and understanding of it, you should not do SCDP. It's not optimal to do that from a machine learning perspective, and it's also not what biology does. Okay, so that was just a small disclaimer about SCDP. I think the community should be, especially newcomers, should be aware that SCDP is absolutely not a golden rule. So from this perspective, in this slide, so the take-home message is that we can really reapply some of the ideas of artificial neural networks, and just like we saw from earlier talk today, that spiking neural networks and artificial neural networks, they don't have to be that different. Right? So in fact, in this case, spiking neural networks can be seen as binary, continuous time, and recurrent neural networks. So a lot of the tricks used in one field can be transferred to the other. And then this, I think, enables a very powerful approach of programming, a high-level programming, like Mike Davies was mentioning earlier. Thinking of TensorFlow, or in general, like Theano, or these machine learning frameworks that actually build a computational graph. So this is an example of a computational graph. It's just doing the simple operation of W, X, and sigma. Once you build this computational graph, so every green box here is a node, so that is, in this case, differentiable. It's very easy to actually go and just take the derivative, right? It's just the chain rule applied on this graph. And what I think makes a lot of the deep learning possible, and I thought this was it was an eye-opener for me at the time, is that you don't have to calculate these gradients by hand. Once you have these gradients set up, you can just basically call this magical gradients function and just have the equivalent graph which computes the gradients of this network. So can we build these differentiable building blocks that are made of neural substrates? Right, so that's exactly somehow what I was trying to tell you here, is that there are models in which you can take the derivatives of spiking neurons in a more approximate but basically a good approximation. Okay, so we can build neural networks and take derivatives of them and basically apply learning plasticity rules to optimize some target cost function. Okay, so in order to do this, of course, we have to look at a particular hardware because, again, locality is going to depend on the particular substrate, which variables you have available at a given neuron. So these are some of the different approaches that are used. And I'd like to, since I did my PhD with Giacomo, so he was not here at this workshop, but he also has this interesting neuromorphic chip, which has 1,000 neurons. And the learning here is embedded, is analog and embedded to the neuron. So a lot of the learning that we saw here, embedded learning, this was all digital, right? So in this case, the learning is analog. This is potentially very interesting because it's not an SCDP rule. They can afford not to do SCDP because the learning itself is a continuous, the synapses are basically a continuous system in themselves. So this is, so they also actually have the chip in 28 nanometers that are built. So this is going to be featured at a workshop in Capocaccia this year. Okay, so we don't have that hardware yet, and it's probably most likely too small scale to actually show algorithms that would impress any proper machine learning like conference. So a lot of what we'll be doing is still in software, but basically a software that is inspired by what we can do in hardware. I'd like to also mention the sentence of Carver-Mead, which is that a lot of our ability now to build neural function is not really limited by difficulties in implementation, I would argue, at this stage. There's a lot we can do in terms of understanding and building the organizing principles in the software over that. Okay, so what we've done here with our colleagues at UCSD and also at the CR lab here at Intel Labs is essentially what we call a neural and synaptic array transceiver. The idea here is that the neural network is a large collection of states which you can couple into 4, 8 groups where every state is essentially going to be like a compartment in your neuron. And the dynamics of each of these states is just governed by linear dynamics, very much like you have in integrated fire neurons and just exponential decay synapses. So that basically allows us to build multi-compartment integrated fire neurons. And we also featured a multi-factor plasticity rules that basically directly uses those state information in order to calculate essentially to calculate the gradients. And we tried to build this whole system without relying on multipliers. A lot of the multiplication is done using bit shifts and fixed point. And we restrict ourselves to 8-bit ways, something that can be achieved with a reasonable size, as we saw, a reasonable chip size as we saw today. And of course, weight sharing at the level of the core, even though it's not biologically plausible, column-nets are not biologically plausible. I think given the hardware constraints that we have, it's still a good choice. So the learning rule here is relatively simple, but it's really drawing from this idea of what gradient descent requires, right? So this was the learning rule. It's the classical chain rule applied to a neuron. So this involves the 3 parts. So one part here, this are the gradients and the presynaptic part. And so the first part here, the derivative of S with respect to the spike, so this is given by a modulation term, which itself is actually a linear combination of the states of the neuron. This makes sense because often the modulation is going to be externally provided, and you want to keep a trace of it until you have a proper postsynaptic and presynaptic spike to make the update. But also because the update themselves can depend on some, in biology, on calcium variables and so on. So this is basically the key. The key approach is really to use the neural components, the state components, as a modulation for the learning rule. And we added to this a classical SCDP rule. So I did criticize the SCDP rule, but since this is intended for a digital implementation, we still need to use SCDP to keep the computations tractable. Okay, so all of this is really based on these two insights. The first one is that we can greatly simplify the STDP weight updates by using just a presynaptic connectivity table. This is pretty similar to how Spinnaker also did its STDP rule in the past. And also involve this idea of this third or external factor, which can be reward, error, or something internal that is computed inside the neural state components. Okay, so with this rule, we can really build different kinds of learning rules. So reinforcement learning, classical reward-based reinforcement learning, that's essentially just where the modulating factor is an external reward. We can do unsupervised representation learning. So this is work I did in the past, showing that essentially if you just have a modulated STDP rule that just switches the sign of STDP, you can do something like contrastive divergence. We call that event-driven contrastive divergence. Sadiq Sheikh, former colleague, showed that you can do unsupervised sequence learning by using some clever competitive learning technique that can also be written in terms of the learning rule we have on our on our hardware. And what I'll be talking more about today is that you can just, of course, do supervised deep learning where the modulating factor is given by the error, and we have these derivatives of the activation functions inside the learning rule. So all of these rules we can do with that inside learning rule. And I have actually another student who's working on implementing ICA with these rules, which also can be written in terms of this three-factor rule. The ICA is for independent component analysis. So for the supervised learning, of course, as I mentioned earlier, one problem is that we don't, deep weights don't have access to the gradients of the top layers, right? So this really requires you to have a symmetric transpose of the weights and plenty of other symmetries in order to do this. So backpropagation is not possible on a neural substrate, so you need to get around it in one way or another. So this technique, which was first published by Tim Lillicrap at DeepMind, essentially shows that you can, if you just randomly project the errors into the deep layers without going through every layer, without doing the whole backpropagation, the results that you get, at least on fully connected layers, is pretty close to what you get with exact backpropagation. And this is great for these neurally inspired approaches, right? Because random weight matrices are very easy to build. If you have analog hardware, you have them for free. Or on digital, you don't even have to represent these random matrices. You can just generate them using pseudo-random numbers locally. So this shows you essentially how we can build this network of spiking neurons. And the learning rule, essentially, that we derive again from these machine learning principles takes this rather complicated form, but it boils down to the following algorithm, which is that at every presynaptic spike, you make an update that t, which is proportional to the error. If the state of the total synaptic input was between two boundaries. This means two comparisons and one addition per synaptic event for learning. So it's very cheap, right? And it's certainly something that you can do with almost any learning rule. This doesn't take into account the history of the spikes, right? So that becomes a little bit more complicated. But it does learn these static spike patterns. So we applied this to MNIST. We can't do much larger networks just because convolutional neural networks involve a lot of neurons and it just takes a lot of time to train it. But at least on MNIST, we find good results. And I just want to focus on this one here, which is showing the error versus the number of operations required to reach that particular accuracy on the task. The black circles are what you get with the spiking neurons. Red and blue are two different artificial neural networks with different sizes. Okay, so you see that essentially the spiking implementation does not require more multiply accumulates, which is the units used in artificial networks. It does not require more synaptic operations than multiply accumulates, right? So there's a parity there, how many synaptic operations you need versus how many multiply accumulates you need. So if you can reduce the synaptic energy per synaptic operation by, for example, doing embedded learning, as I mentioned in the beginning, this could give you a huge payoff, right? The synaptic operation is fundamentally easier. There's no multiplication involved. Right. The errors that we get there, at least on this hardware, it's a small network, but it's in the 4%. If you implement this on floating precision, you get in the basically 2%, 1.8% error, which is perfectly reasonable for MLPs, fully connected layers of this size. We also applied this. I'm going to go quickly over this. I'm sorry, I see Brad standing there. One of the issues of restricted Boltzmann machines, as we saw earlier, is that it requires symmetric connections in order to work properly. And this is just, again, it's almost the same problem as you have in backpropagation. So natural question is, well, does this idea of random backpropagation work also in these restricted Boltzmann machines? And the answer is yes. So we get similar behaviors here. So if you have a random feedback matrix, this this also works in these more recurrent restricted Boltzmann machine style networks. So this was done by Georgios Teterakis, a postdoc in my lab, and also by Travis Bartley, who's here. And finally, so you can apply the same idea for sequence learning. And this was interesting work that was done by Friedemann Zenke along with Surya Ganguly. And in this case, it really learns a particular spike train. So learning to do the exact spike times. And this also works on this neuromorphic platform that we are developing. Okay, so final notes is that so computing on a physical substrate, well, it requires local algorithms. In particular, if you're doing spiking neural networks, well, that it's the particular, you're constrained by the neural substrate there. Backpropagation in physical substrates is easy, or approximate versions are easy if accuracy is not, absolute accuracy is not your target. So if you really think of neuromorphic hardware and algorithm code design, well, three-factor rules and this modulated CDP-like rules can be very useful. I was going to skip that and just point to two workshops that I'm helping organize. So Mike Davies mentioned one of them, the Telluride workshop. So you see Kwabenabua here in the background. That's because he's there all the time. So the topic here is going to be embedded perception and action. So it's really the kind of work that's being done here. It's going to feature some Intel Loihi hardware as well. And earlier than that, there's also a European version of Telluride, which is happening at Capocaccia. And I think so here we're going to have on the analog chips from Zurich, and also the Human Brain Project will be there with actual hardware. I would like to focus on these two workshops for their hands-on component, right? They're long, they're 3 weeks and 2 weeks respectively. And that gives you plenty of time to actually start using this hardware, in addition to really awesome discussions. Slideless discussions for Capocaccia, so people are forced to explain things with their hands. All right, thank you very much.
We have time for maybe a question while Sam comes and gets it up. Quiet.
It's the lunch effect.
Oh. All right, well, thank you, Emre, again.